In this video we're going to look at how to extract a line scan from an image. And the objective in extracting a line scan is to measure the dimensions for these features within the image and therefore determine the lateral resolution that is possible within this image. Once a line scan has been calculated from an image, the next problem is to estimate the edge resolution for these features. And one way of doing this is to identify an edge and then make use of a background type that will give us some statistics about the width of this edge, and that is a D parameter background type. When initialized, the first value in the cross section indicates the value between 0 and 1 that is the threshold used to calculate the interval over which an edge rises. So this is making use of 88% or 12%, as to say when the signal rises by 12% the first point is calculated, and after it's risen by 88% then a second point is calculated, and the difference between the distance between these 2 points is a measure of this edge resolution. The problem with collecting a line scan based on individual pixels is that the signal to noise tends not to be terribly good for image data. So what is required is that a number of pixels are summed in order to produce a line scan. And the options that we can use to do this are on the VAMAS info property page in the edge resolution section. So if we draw a box and then we set a zone, then we can see the set of pixels that we would sum in order to produce a line scan. And the way the line scan would be calculated would be for each pixel in the horizontal direction, the pixels in the vertical direction are summed to produce an intensity within the line scan. If a line scan is calculated based on this box and this image, then the line scan would not be representative of the lateral resolution. And that's because the features within the image do not align with the box. So before we can calculate the line scan, we must rotate the image so that these features align with the vertical. When the Create Zone button is pressed, a zone is added to the history for the VAMAS block, and the history of processing for the VAMAS block is on the spectrum processing dialog window, and you can see here it indicates the image zone and the dimensions for this box. And what we would like to do is see the full image to allow us to specify a direction that would be appropriate for rotating this image. So I'm going to undo the operation, and now we can see the full image again. To create an image that has been rotated, we use this rotate button, and what we need to do is specify a direction that represents a direction that we would like to make the horizontal. So having indicated a line, I press the rotate button, and then a new file is created, and within this file there's a rotated image. And so at this point we can now specify a region and then press the create button. And if we assume that these have now aligned with the vertical, and perhaps on another occasion I could have done it better, but for the purposes of this video I'm going to assume that these features are now all aligned, and I've selected a box that I would like to integrate to form this line scan, and having indicated one of these boxes I can then say line scan from row box, and as a result we get a line scan which, if we display in kinetic energy, that we now see it says distance. So this is the distance that was determined by the micron bar that was on the image, and these represent the features that we might now wish to analyze to work out lateral resolution. We'd like to measure the width of these features, and the features that we're interested in are not the peaks but actually these troughs. So if that's the case, then what we can do is introduce a background and make this relate to the top of these intensities, and then we'll select one of these features and measure the width by introducing a component. And the component, because we have a negative going intensity relative to this background, is an inverted peak, and I can change this to be an SS, which is a top hat function that is created from two top hat functions that are convoluted together, and they're of different widths. So as it stands, I have a convolution that is producing a shape that is not quite fitting these data, but if I introduce an iteration which will increase the number of convolutions of these two functions, then I start to get a shape that is more compatible with the data, and I end up with a fit here. And looking at the full-width half maximum, it gives us a measure of the width of this feature. I'll just illustrate some of the features that are associated with the display of zones over images. The zone that was created previously blanked part of the image. Let's just illustrate that by creating a zone here, and the box is marked and everything outside the box is set to a blank color. However, this is because of the mask buffer scale type, and these are the different color scales that are available, and there are two that will have this influence on the display of the image. So if I use the false color scale, you can also see that while the colors have changed within the box, outside it's still blank. However, if I go to a grayscale or a color scale, you can see the full image and the box is simply marked. Another feature of these zones is that when we calculate a line scan, the line scan will not just only be calculated for the one box. So if I create another zone, dragging out a box, and I say create zone, there's another zone that will also create a line scan. I could even create a zone within a zone. So let's create a narrow zone that is also within the first zone. So we can see the relationship between the number of pixels and the signal to noise that we see in the line scan. So I'll now create 3 line scans, one for each of these 3 zones, and if we overlay these, we can see that we have now 3 line scans. The third one and the first one both came from about the same area, but you can see that the green one has poorer signal to noise. You can see greater spikes in the data compared to the red one. The counts per second actually means counts per second per row. So if I change from counts per second to counts, then you can see that the line scan that was created from the narrower zone has fewer counts, and the line scan from the wider zone has greater counts. So converting to counts per second allows a comparison of these data.